Astronomers believe that on average, we should see a supernova in the Milky Way every 50 years. When you look out at other galaxies, that's about the rate that you see them happening. And yet we haven't seen a supernova here in the Milky Way since the 1600s, the famous Tycho supernova. And so we are well overdue. It's believed there's one potential supernova remnant that might have happened in this time and just nobody observed it. But still, where are all the supernova? And when the next one happens here in the Milky Way, we will be ready. And not just in the visible spectrum with our telescopes, but we now have neutrino detectors. We have gravitational wave observatories, ways to find out about the supernova before it's visible in the sky. And my guest today is Dr. John Banovetz. He's a postdoctoral researcher at the Lawrence Berkeley National Lab, and he worked at Brookhaven National Lab. And his most recent paper is about, wait for it, how Rubin will help us do follow-on observations of that next great supernova that's going to happen here in the Milky Way. That you're going to get this gravitational wave alert, you're going to get this neutrino alert, and then you're going to see the supernova start to explode in the sky. And Rubin is the right tool for the job to be able to zero in on the right location before the supernova is visible and catch the very earliest stages of this detonating in the sky. So if you want to hear some practical ways that Rubin can help astronomers push science forward, enjoy this interview with Dr. John Banovetz. John, when was the last supernova in the Milky Way that we are sure of?
Last one that we are sure of would be Kepler's supernova in like the 1500s. There was one, there's a famous supernova remnant called Cassia that we thought we know exploded about 300 years ago. However, it was weird because only one person saw it. Usually you have these supernova and you have multiple different observers from across the world that are able to kind of have records that show that the supernova existed. And for Cassia, there was just one. And then we've just been sitting, waiting for like even from Cassia, like 350 to 400 years, waiting for the next one to come up.
How often should they be exploding?
So the number that you probably hear most often is about 2 per century for the Milky Way. This is from looking at different galaxies that are similar to the Milky Way, along with like stellar formation. So how often like stars form and how often like massive stars form in galaxies. And there's even a way of looking at the radioactive aluminum on Earth, because that is produced by supernovae, and looking at how much of that we actually have. They all converge to about 1 to 4-ish, with most of them going to 2. Now, you'll hear like 2 per century. So like you might think 1 every 50 years. It's probably closer to 1 every 100 years, just because we are on one side of the Milky Way. There's a bunch of dust and other things on the other side. And so it sometimes gets reduced down to 1 per century, just because a coin flip of, is it on our side or is it on the other side?
Right. Yeah. So like we've got the dust lanes in the center of the Milky Way that's obscuring our view to the other half of the Milky Way. Like the zone of avoidance is preventing us from observing the events that are going off on the other side of the galaxy. Okay.
Exactly.
And you know, obviously like the most recent supernova that we have on record was 1987A, and that went off in the Large Magellanic Cloud. So that is close, but not close enough for us to be able to make the kinds of observations that we want.
Yeah, we want to be able to get as many observations as close as we possibly can, especially during this age of like multi-messenger astronomy. So a big thing right now is the upgrades of neutrino detectors. We have like Juno and Super-K and IceCube that are be able to look at extragalactic neutrinos in some cases. They will be able to pick up on supernova and tell us a whole slew of science about the actual explosion. There's even talks of gravitational wave detectors. If the supernova is close enough, that we'll be able to actually get a signal before the supernova goes off. And both of these things are really important in getting kind of the scientific community ready for the supernova. both neutrinos and gravitational waves should happen before we see the light. And so there's like the supernova early warning system, or snooze. They're starting to they've been set up for a long time of what happens if a supernova goes off. How do we point all the telescopes there that we need to point? How do we get the location and stuff like that?
Right. And I guess I should clarify the audience, because I know I'm going to get these questions from people after. Why do we get the gravitational waves and the neutrinos before we get the light of the supernova?
So for the gravitational waves, just a little bit into how a supernova explosion happens. You have the star, it essentially loses all of its fuel. And so you would have kind of light. You'd have gravity pushing things down, light forcing things up. If all of a sudden you lose the fuel, you're not producing light, everything comes crashing down. And so if you get a mass enough star, that can cause a neutron star to form. And with the gravitational waves, what's interesting is you will essentially have this really heavy, like on the order of 1.5 solar masses object that possibly could start sloshing. And so there's instability called SASE. And so this sloshing then causes gravitational waves to form. And so if the object is close enough, that will happen before the bounce back from the matter that causes like the supernova explosion.
And you don't necessarily need a like an asymmetrical burst off the supernova. It could just be that as this process is happening, this neutron star is sloshing around inside this mess, and that's getting you your gravitational waves. Okay.
Exactly. Yeah. And so that's one way how we would. And so once the bounce back happens, you have this explosion. However, there's still a lot of stuff falling in that it needs to get through. And so we don't necessarily see like photons right away. However, neutrinos don't really interact with anything. And so they can just go right through at the speed of light. And so one of the actually interesting things when combining neutrino and the electromagnetic or E&M part in light is the delay between when you get a neutrino signal and when you get the light, because that actually will tell you the radius of the star and how big it is.
Right. Oh, that's really cool. Okay. So you get sort of the gravitational waves come first because they're moving at the speed of light.
Yep.
The neutrinos come next because they're moving like just shy of the speed of light, but they're able to escape the star before the actual electromagnetic radiation does. Then finally, weirdly, you get the light.
Yep.
That is finally able to escape the explosion and make its way out to us. Do you have a sense of like what that delay is between those three events?
So the delay between your kind of sloshing and the explosion, I think, is on the terms of like a few hours or something like that. It's really, I don't know, supernovas explosions are really interesting. You have this star that lasts for billions of years, but then as you get closer and closer to the explosion, everything ramps up incredibly. And so, you have like a few hours. And then in terms of the delay between the neutrino signal and the light, you have anywhere from seconds to milliseconds to days. It really depends on how big this thing is. So there's a few kind of like what are called progenitors, the thing that causes the explosion. One is a red supergiant, this kind of massive bloated star. And so it takes a long time for the light to actually get through all of that material. And so that's where you get like the days. However, there's these really, really massive stars, like 40 times the mass of our sun. They have a really small photosphere. They've already shut off a lot of material just by rotating really fast. They're called Wolf-Rayet stars. And so it's really quickly that the light can get through. And so that's where you get like the seconds to milliseconds. And then you just have a host of things in between of different sizes and stuff like that.
Right. And so let's talk about why we're not seeing them. Why do we think that we have not detected the number that we should? 4 centuries, 5 centuries?
Yeah. So one of the reasons is something that I just mentioned earlier, which is maybe it's happening and it's just all on the other side of the galaxy. We're incredibly unlucky. We just can't break through. And then another reason could be that, as I also just kind of mentioned, is that things are like shedding mass as like the star evolves. And so what can end up, sometimes there's a theory that what's happening is that that creates a kind of a dust cloud around your star. And the dust is really good at absorbing light, which is why we can't see on the other side of the Milky Way. And so maybe things have exploded like Cassia or something else, and there was just so much dust around the object that it actually obscured the explosion, and we couldn't see it, at least back in like the 1600s, where we just had our eyes to look at it. And that's the other exciting thing is that, I mean, 400 years is a long time. You think of like the technological advances that we've had and stuff like that, the development of like the modern telescopes and things. It's only been relatively recently that we've had like CCDs and we can observe things that are outside of the optical wavelength. And so it could have just been it exploded, but it wasn't visible to the naked eye. The final option is our models are incorrect, and the rate that we think happens doesn't happen.
Right. I mean, I was sort of thinking, like, I know there's sort of this growing evidence for possible direct collapse black holes where they don't produce any kind of supernova. But again, like, you wouldn't also see those going off in other galaxies. So that doesn't help.
No.
Are there other objects, like Cassia is a sort of classic example. It's the kind of thing that, you know, I've been able to catch with my telescope, but I'm sure my audience is able to take images of it. Are there other objects that when you look at them and consider them, maybe with other clues, like other wavelengths, radio waves, all this kind of thing, that they're, you know, a rapidly spinning neutron star that might be evidence for a recent supernova? Is there anything else out there that people say, well, maybe these are the ones that fill the gaps?
Yeah. So there's the Crab Nebula is the other kind of major example. That's obviously earlier in it exploded in like 1054, well documented. Finding the neutron star has been actually very challenging. Some of my PhD research, it was into supernova remnants and things like that. And you have these explosions where we're looking for neutron stars and we just like can't find them in most cases. There is one in the galaxy that does have a neutron star. Unfortunately, it did not get a cool name. It was G292 plus 1.8.
Right.
Great name.
Yeah, classic pulsar name. Yeah.
Yes. Exactly. And so that it has a pulsar with nebula in the center. And then you have things that we don't necessarily have like the neutron star for, but you can see it actually to kind of penetrate the dust cloud. You can see it in like radio or infrared or X-rays. And so there's these really kind of young ones that are in X-rays closer to the galactic center that some people have estimated ages of like 100 years. So this would be in like your 1800s, 1900s, where we didn't really have like the means quite yet to like get an X-ray detection in the center of our galaxy. But if it happened now, we'd be able to like follow it up and with like the better telescopes and things like that.
All right, so let's get to the meat of your paper then. So you are proposing that Rubin, which I've been doing interview after interview about Rubin, which, you know, can do anything, could also help us find that next supernova.
Yeah, so the Vera Rubin Observatory is just, as you probably know, and all the interviewers have said, a fantastic observatory that everyone's just super excited about and super excited to get their hands on the data for. One of the things that we're excited about with Rubin is that it can go really deep in relatively short exposure times of like going up to these really dim objects at high magnitudes of like 24th meg in like 30 seconds. And so I talked before about like how we haven't been able to penetrate the dust in the kind of the center of the galaxy and be able to see stuff on the other side of the galaxy. Well, Rubin can go really deep, really relatively quickly. That'll be important later, that I'll just mention. But it also has access to these infrared wavelengths that can kind of go detect things past the dust. And be able to get these objects. And so the other thing that Rubin's really good at is slewing. which might sound weird of like, why do you care if a telescope moves really fast or something? But you get these, essentially what will happen that we were trying to plan for in the paper was we get this neutrino signal, and we're specifically looking at Super K, gets this signal, says, we think that there is a supernova happening in like this region. And everyone's like, great. Sometimes that region, for Super K, it will be small. Sometimes that region can be really big, like with gravitational waves where it's like thousands of degrees on the sky. So Rubin moving really fast, we can get on the object as quickly as possible. And then we can also take really fast images that go really deep so that we can tile and get that entire search area at a relatively quick time scale.
I see. So you get this warning from the the warning network from the neutrinos, and then if it's up in the southern sky at the time that Rubin is operating, then you just start scanning around in that region looking for the first moments. Because I guess the hope here is that you get that opening seconds of watching the supernova start to unfold.
Yeah. So one of the important things that we really want to get, and it's really difficult to get for supernovae, is this thing of shock breakout. So I mentioned before, you have the neutrinos come in, and then you have the light. That first little bit of light is called the shock breakout. And so if you know when the shock breakout happened and you know when the neutrinos happened, you can tell a lot about what kind of star exploded. You can get like the radius, sometimes the mass, and things like that. And so we really want to be able to go there really quickly and be able to capture this one moment.
Right.
And yeah.
And sorry, so like how much uncertainty does the warning network give you? So how much of the sky do you need to scan with Rubin?
So with Super K, we'll get at something like 30,000 light years, we'll be able to get 6 degrees, which means, I don't know, for me, if you're not an astronomer, it's hard to imagine what does 6 degrees look on the sky, but it's like a few times greater than like the moon.
Yeah, 12 by 12 moons.
Yes. And so Rubin has a field of view of 10 square degrees. And so we're kind of perfectly matched up to be able to go right on it. I mean, again, so the search area goes up the further away it goes. So if it's not at like 30,000 light years, then the area gets bigger. But Rubin kind of perfectly matches up to be able to image sometimes the entire area right away in order to search for these like important events.
Right. And if it's farther, or if you're more uncertain, you can just be sort of like doing a flower petal around and try and make sure that you've got it. And then if you do get it, then boom, you just switch and that's it. So, I mean, that sounds like a very exciting use. Does this code exist? Is there this connection yet between the warning network and Rubin so that it will automatically chase down this potential supernova?
We are working on the code. Sean McBride is working at Vera Rubin Observatory to implement not just what happens if you get a neutrino alert, but also gravitational waves. He led the follow-up along with a bunch of other people of a couple of gravitational wave events. And then one of my collaborators, Claire-Elise Herbert, is working on the code of how do we actually know it is a supernova, because if you just take one image, there's going to be a lot of things in the sky that are changing. So how do you know which one is the supernova? And so you also have to take multiple images, start to rule things out. And then you also have to be able to kind of subtract out known things really well. So there's a lot of the science nowadays is what happens with template subtraction. So you take an image of the sky multiple times, you kind of know what the static sky in that area looks like. You take a new image, you subtract your template from the new image, and then a bunch of new stuff appears. And so she's doing a lot of work on how to subtract that out correctly in order to find out where the supernova is, because it could be hiding behind a star. And if we just look at one image, you might not be able to see it right away or something like that. And so
It's interesting. This sort of is very similar to the Kilonova event back in 2017. 2017? Oh,
Yep.
so long ago.
Yeah.
Where, I mean, you got this multi-messenger alert where you've got the gravitational waves and the electromagnetic signal coming from two colliding neutron stars, and the world's telescopes turned on this thing and imaged it in essentially real time. And it's that same issue where you've got this very, as you say, thousands of degrees, it's kind of over there, that away. And then you've got to try and catch that. And so, have the gravitational wave measurements gotten better since then to give you a tighter field that Rubin can focus in on?
So for the gravitational wave events, there'll be a tighter field, mostly because you're only sensitive to that kind of sloshing at right now relatively very small distances. I say small, it's about like 3,000 light years, but you're only sensitive to about there. And so what the paper mostly focused on was the neutrinos, because there we can already reach to like nearly the far side of the galaxy. And so the idea is if we get something from this sloshing, most likely it's a star that we know of and a star that's really close by. So Rubin can image it, but also that opens up to like hundreds of other telescopes that are able to go there and start imaging things and get measurements.
Yeah. And theoretically, Rubin will have already seen this star who knows how many times in the past, as it's moving through its, and so maybe you'll get some signs of what it was doing before it detonated, which would also be really amazing.
Yeah, and that's one of the beauties of having a 10-year survey is that if we hope it happens towards the end of the survey, so we have a lot of data, we also have time to set everything up, but it also means that we would have an invaluable data set of what happens to a star years before, because there's a lot of science going on of like, is there like what's called eruptive mass loss? Is there already years before, is there already some instabilities in the star that's just causing kind of mini explosions that's releasing a bunch of mass of the area? We're not sure. There's a lot of evidence in, I think, especially the radio that it is happening, but it would be fantastic to be able to get that light curve and see when that happens. And so,
yeah, because I mean, I know that there have been these surveys done with Hubble or with James Webb, but you're looking at other galaxies that are tens of millions of light years away, and you're seeing, we see a supernova, we've identified the precursor star, and it is 1 pixel, and it is very far away, and we have, very limited information about that star. But to have hundreds of observations of that star here in the Milky Way from Rubin, capped off by, and then it blew up, that just sounds like the dream.
It's not only just with the star, but if it's close enough, we can tell, is it in a binary system? How is that interaction coming into play? Because that's another kind of big thing in supernova physics right now is a lot of the models, you start off with a single star, but we know that 50% of stellar systems have multiple stars in them. And so it's starting to get into how much does this binary interaction play into a supernova explosion. And so it would be awesome to have, a 10-year light curve coming up to the explosion, as well as definitive, we know that this isn't a binary system. We know what the binary star is because, again, as you kind of mentioned, we have these images from Hubble and other observatories of like supernovae, and also kind of like estimates of what the binary is. There's been a couple of cases where Hubble's been able to put limits on what a binary would be, as well as in some cases directly detect a binary, but there's still like huge mass ranges and things like that. And so to be able to get an up-close personal experience to the star before it explodes would be monumental in the field.
Yeah. Oh, that's exciting. All right, John, I'd like to shift gears and talk about your work with the pipeline. And I have been, I did a interview a couple of weeks ago with one of the data brokers, the people behind the Antares system, which are
Hmm.
sharing information from Rubin. And we've reported a little bit on Universe Today about some of the fallen observations that people are doing, but this is brand new. Like we are now, people are dealing with the Amazon River of weird flickering things that are happening in the universe and trying to wrap their minds around it. So what has it been like for you as an astronomer to actually work with this stuff?
It's been really, I don't know, indescribable in some cases. There's just been so many different alerts. I think, yeah, you're right. They just started releasing alerts a couple months ago. And right now I work with a new observatory, DESI, the Dark Energy Spectroscopic Instrument. And we've started to do our own follow-up on some of these events. And so I think we were one of the first people to have discover a supernova from one of the Rubin alerts. We have a spectra and we've classified it. But it's been, I mean, awesome to be able to get just the huge, even like Rubin's already coming out with this huge plethora of like alerts just from this relatively small area that we have. It's just been incredible, and I can't wait for it to expand into like the full survey and just see how many things are happening in the universe.
So how do you sort of define your criteria that there's 700,000 alerts that are coming through the system every single night? You have limited time on the DESI instrument. How do you decide, or how have you set the criteria for, okay, out of the 700,000 that happened to this night and the next night and the night after that, we want this exact kind of thing that will then do some of those fallen observations? What are you looking for?
So yeah, there's a few of the what we call cuts that are applied. And so one of the things that's nice is I believe most of the brokers and if not Vera Rubin Observatory itself already is like, okay, like we know that this is a solar system object, right? Because with DESI, what we're looking for is what's changing, and then what's Rubin saying is changing in the night sky. And so there's a huge number of things that it could be. It could be just an asteroid passing by. But we have, I mean, just from the Rubin first look, we have a huge number of asteroids that we already know about. And so there can already be some filtering of like, hey, we know that this is an asteroid, or we know that this is a variable star, or and stuff like that. So you can already do some cuts on that. However, if there's something new, what we generally just do is, has there been, first we do a magnitude cut. So if it's too dim for DESI to see, we don't try to observe it.
And where do you make that cut?
That cut is limited to DESI. So right now we're at 22.5 just for kind of the observations that we're trying to do. We could expose for longer.
I let my audience know, like, even with like a backyard telescope, I've got a couple of even smart telescopes behind me. You can get down to like 15, 16 if you've got nice skies and you do a nice long exposure. And there are events that are in that magnitude coming up out of Rubin. Like they're there. You can do your own follow-on observations if you want of these objects. And so for you, 22, that still feels like it's a large number. Like you're probably still getting thousands, if not tens of thousands of objects that meet that criteria.
We're getting not quite that much, mostly just because right now the alerts are just coming out of two fields. So the what's called the Cosmos field, which is in the sky right now we can observe, and what's called the XMM field. So the thing that we have to worry about is, unfortunately, DESI is in the north, Rubin is in the south. There's not a lot, there is some overlap near the like equator, because DESI can go down to like minus 20 dec and Rubin can go up to about plus 20 dec. So you do have some overlap, but between the alerts just coming out of the deep drilling field and that little bit of overlap, we do still have hundreds of alerts, which is awesome. DESI has like 5,000 fibers on it, and so we are all set to go to try to observe these alerts. Like pretty much we can almost do a pointing and get most of them. And so that's incredible. But yeah, so for right now, we're in the hundreds, and which is why very exciting and can't wait for the full survey and the full alert stream to come up, because then we're going to be getting thousands of alerts that we can follow up on.
Right. Yeah. And yeah, I know it's going to go up by like a factor of 10, I think, by the time it sort of reaches its full operations.
Yeah. I mean,
just madness.
10 million a night.
Yeah. Right. But you're looking for, I mean, is there let's say it's been up to 3 nights since Rubin has looked at an area. And so it kind of means that it's been up to 3 nights that the supernova has gone off if it's in that one of those fields. So is there any indication of how new the supernova is just by pulling those images? Because I'm assuming that those are the ideals, the ones that literally have gone off while Rubin happens to be observing in that field, ideally, or just moments before. Can you get a sense of that from is it like the light curve or something?
Yeah, so there's a few things that you could get from the light curve to kind of tell you the age of the supernova. However, we're definitely, we want to get the earliest light curve possible to see as what happens as soon as the supernova goes off. You can, with 3 nights, you can kind of tell of like, okay, the general supernova light curve, you go up, you peak, and then you kind of slowly start to decay back down. So with 3 nights, you can kind of tell, okay, have I like peaked? Am I still rising, or have I started to decrease? And that can tell you what kind of stage of the supernova that you're in. And then there's a lot of very smart people working on, okay, how do we, if I only have these 3 points on the tail end, how can I reconstruct and tell you when the supernova exploded, give you an estimate on the mass, the energetics, all that stuff.
But you can, I mean, this is the part that's crazy to me, is that you can, you detect a supernova in the data information, you get another one, you then calculate that, you look at the light curve and you go, it probably went off on this day. And then you go, again, here's the magic. You go back through Rubin to that date and blink between the two and you're like, yep, there it is. Right?
Yeah.
So let's send the time machine back and let's begin our observations on that supernova when it went off, in addition to doing all our follow-on observations with DESI and so on. And so you'll hopefully be able to kind of tighten that response time down.
Oh yeah, no. I mean, with the cadence of Rubin, 100%, like it's you tile the entire sky every 3 days, and so you can imagine you have what we call is a cadence of like how often in that light curve are you sampling it? How many times do you get an observation every 3 days in order to fill it out? And so, yeah, you can, I mean, you now have a window of like, yeah, it's plus or minus 3 days. And that's not including things like it's you generally in just 1 or 2 filters. And so you're going to get observations in between those 3 days. And so you're definitely going to be able to narrow it down and be like, it exploded here, which is going to be awesome in understanding everything.
And I'm assuming that the goal in the end is we want to see the supernova within minutes, within hours. Like we really want to shorten that time down. And it's just a matter of getting lucky with when Rubin makes the observation and when you realize what it is that you're working with. And that is that skill to sort of, is that sort of technique that you guys have to build up?
Yeah, there's still some technique in looking at a light curve of 2 points and being like, yep, that's a supernova and things like that. However, even if we're like a little late, the power of doing these spectral classifications with DESI is we then like for sure know it is this type of supernova, and is going to be invaluable data for when Vera Rubin goes and the legacy survey of space and time begins, because then we'll be able to train AI machine learning algorithms to kind of do it for us, because I I like looking at light curves as much as the next guy. I cannot look at 10 million a night, and I don't want to. And so to be able to, and some of these brokers already have these kind of classifiers and these machine learning things set up, but to improve that based off of like the DESI spectral classification is going to be invaluable in determining, oh yeah, this is this type. And then that way, once we're done in 10 years, even if we don't have a spectra for all, oh man, it's going to be like 10 million to 100 million supernovae, which is crazy thing to think about.
Yeah.
Because
and I know like even like over a million just type 1a supernova.
Yeah. And exactly. And so you'll have all these supernovae, but you might not have spectra for them. And so we need to be able to get the data to train these algorithms so that they can sort out what is actually supernova versus another transient event.
And is there like one event, is there some kind of event that you would be most excited to see? Apart from the one in the Milky Way, like obviously that would be the great, like Betelgeuse goes off, we're all excited.
Yes.
But is there some kind of more obscure sort of scientific possibility out there that you would hope to be able to go like, we're looking at it?
Yeah. So there's one of the exciting ones is there's this new class of supernova, which I don't know. We come out, we find these new exotic objects every year, and it's crazy to me that we're still discovering so many things. This one in particular is called an FBOT. It's a fast blue optical transient. And so I mentioned before how you kind of have this light curve, and it goes up and down. That's like on the time scale of days. For these objects, it's like within a week, it is up and down. And so you have like very limited time to be able to catch them. But again, with Rubin's cadence of 3 days, we're going to be able to detect a lot more of these, follow up on them, learn what's happening in that area. And then I'm also just excited for the supernova 1As and the amount that we're going to get, because we have all these in cosmology, all these constraints with supernovae on the cosmological parameters that are off data sets of 1,000 to like 2,000. And as you said, like Rubin's going to get 1 million of these. And so that's one of the things I'm excited about is right now, and with supernovae, there's all these subclassifications and stuff, but we're only getting about, I think it's something like 1,000 to 10,000 supernovae a year, which sounds like a lot, but it's still kind of a very small subsample, and we're discovering new exotic objects. So I'm just excited that we're going to have this huge database of supernovae to look at and be able to classify things, what's weird, what's a normal thing, and stuff like that.
Yeah, it's like whenever you take a larger sample, then new weird things are seen. I know there was these sort of sub-classifications like supernova 1AX. Like maybe there's examples of type 1A supernova going off inside the atmosphere of another star. Like things can, if you have a big enough sample of the universe, weird stuff can happen. I want to give you a name. So there's the FBOT, the fast blue optical transit. That's a terrible name. And the astronomical community needs to get off this name. My audience, one of my commenters on one of my videos had a recommendation, which is a blooper nova. So I just want to throw that out there as a possible name for the FBOTs. If we can move to blooper novas, then I think it'll turn it into one of the more kind of charismatic mystery objects out there. I'm just throwing that out there.
Yeah, blooper nova is good. The fun thing with FBOTs for a while was I think they stopped doing it. They all used to be named after animals. So the first one was like 2018 cow, and then there was a camel, and then there was a snake. And so
they were trying to go after kind of charismatic megafauna of
yes.
But I think a general thing, that's just hopefully we can make this one go. So anyway, John, a question I always ask my guests: what are you obsessed with right now?
Right now, I am honestly as obsessed with just astronomical surveys in general. It is crazy to be in this era of kind of like big data, and I'm working on like different pipelines and stuff like that just to be able to process all this information. Like we have Vera Rubin coming up. DESI is about to be extended, I think, into DESI 2. And then we have SPEC S5, which is another spectroscopic survey. And then we have Roman, and then we have Euclid, and then we have Spherix. And I will say it's just incredibly nice to have almost too much data to work with. I would rather have too much data than not enough.
Yeah. And it's at a time where there's a lot of sort of machine learning clusters being built for chatbots, which then all those companies will go out of business, and then there will be massive compute available for doing machine learning on characterizing astronomical objects. So I think we're at a sort of perfect time where we're going to have plenty of excess compute at the same time that we have these enormous data surveys where we need to be able to grind through them and get some answers. So I'm, if the AI economy crashes, it'll be a boon for astronomy.
It'll be great.
Time they need it. Yeah, totally. Well, John, absolutely fascinating. Good luck. I cannot wait for, like, it's Betelgeuse, right? Betelgeuse when's it going to go? Tomorrow?
The famous quote with Betelgeuse, tomorrow or 10,000 to 100,000 years.
Right. Okay.
Place your bets now. Get the betting pool ready to go.
That sounds good. Yeah. I'll put that bet together. All right. Well, John, thank you so much. Good luck with your research, and I can't wait, as I said, to see that next supernova. Take care. I hope you enjoyed that conversation with Dr. John Banovetz. Now I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caroline, Chuck Hawkins, Commander Bielek, Darkfinger, David Gilton, David Matz, Evan Pro, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Sutz, Michael Purcell, Nordspace, OneStepForAnimals.org. Follow my nephew at VBrick6994, Ren Kaidu, Richard Williams, Sean Sargent, Team Fowler Monthly, Team 49, Telescopes Canada, Vlad Shiplin, Wolfgang Klotz, and Zelda Borg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. Well, this was great. I am, really excited about sort of practical uses for Rubin. And this is sort of like how my reporting is probably going to be shifting over the coming years. We've had this phase where Rubin is just around the corner. We're about to see it. This is great. Here's what we could get from it. And now the reality has arrived that we're seeing hundreds of thousands of alerts every night. And this is just the beginning, that these numbers are going to ramp up to millions of alerts every single night. And yet astronomers are going to have to do the practical work of sifting through all of those data to find the events that they're excited about, that they want to do follow-on observations, and then do dedicated time on other telescopes to actually make those observations. This is where the rubber hits the road. This is where the practical experience is going to come in. And yet, because of this, we are going to find and discover new things that the universe was doing when we weren't looking. And so do not be surprised if you get a lot more of this. Yeah, but how are you wrestling this enormous amount of data interviews in the coming months as we go? And then I'm sure it'll shift to hear all the incredible new discoveries that we made and how did you find it? So this will be the timeline, the stories that you're going to see coming out of Rubin as we go through the next couple of years in this sort of entirely new age of astronomy. And hopefully you're going to be enjoying this as much as I am. All right, we'll see you next time.